I think what we're going to do here is we're going to look back at this task. So I think everybody remembers this task from when we met a couple weeks ago. If you don't remember, this is the stereotyping task, or as we call it in the sample from the Clarion Library, the identification task. It's not really a task. The task itself is not actually it relates to stereotyping, but the actual task that the agents perform is an identification task, of course. So just a reminder of what we saw in this. Participants were placed into two groups, a private group and an anticipated public group, where they would be told that their results on this identification task were going to be shared with the other members of the other members in the room. They were primed. A flash on the screen of either a black or a white face was presented, and then it was followed by a target item, which was either a tool or a gun. And what the findings found was that counter to what your intuitive thought would be, that actually people in the anticipated public group made more stereotyped responses. That is, particularly when a tool was paired with a black prime, people were more likely to misidentify the tool as being a gun than they were when they were primed with a white face. So the idea, and that was especially in the anticipated public group. The idea behind that was that there was a system of, there's a process dissociation that's going on. That is, people have limited cognitive resources, and when you're placed in an anticipated public setting, you have a limited ability to be able to deal with both the pressure, the anxieties of social social-related anxiety cues, as well as this task, which was a very rapid response task. People were given only about 400 milliseconds to respond, so it falls right in that time, or that capabilities where it's either, or it falls right into that space between being explicit and purely reactive. So this ability to be able to make controlled responses requires a lot of cognitive resources in order to be able to perform. So,
sure. Can you go back to the bots underneath it?
Yeah, this one?
Yeah.
So, continuing on with what I was saying is that when those resources were inhibited, people tended to make more reactive type decisions. And these reactive decisions are more implicit in nature, the idea being that people's experiences within society of black individuals being paired with violence or crime or guns would cause that association to be strengthened, and would make people cause people to make rapid bias responses, whereas more controlled processing would allow for that biasing to be filtered out. So Jacobi came up with this way of dissociating responses in a natural type way, without having to either, or without having to, I guess, dig inside of a person's brain. You could make estimates about what a person's cognitive control was based on how they responded, as well as make estimates about what their accessibility bias was, or what their implicit stereotypic biasing was. Within Clarion, though, we can capture this kind of thing by looking at the integration between the top level, by looking at how the top level and bottom level are decision making are changed or affected by aspects of motivation. So in this particular case, we used a single drive in the MS for honor, relating to people wanting to adhere to social norms, or capturing a propensity towards being affected by trait anxiety, by task anxiety or social anxiety in this particular setting. In the MCS, what we did is that the honor drive would then be affected by that, or the honor drive would then affect your ability to make controlled responses in the top level of the ACS by tweaking a top level versus bottom level parameter, and that was along an inverted U curve. So the idea being that the top level of the ACS would have fixed rules where there was no prime features and there was only target features. The idea being that these rules were obtained through a series of practice trials that occurred before the targets appeared on the screen, and reflected controlled responding. The bottom level was neural networks where both the characteristics of the targets and the primes were placed in the system, and the system was pre-trained to make responses mostly based off of the prime features and in particular the skin color. So real quickly, there's a look at what the graphs look like that are capturing it. The idea is that this is drive strengths. The public group has higher drive strengths than the private group in terms of this bottom line, which is a predisposition towards anxiety, just individual differences, inherent sensitivity. And the MCS had this curve where at low levels and at low to medium levels, right in this area, in fact, if you notice, this curve very slightly bends upward, that cognitive control actually becomes a little bit higher, so you can actually, if you're influenced a little bit, you just got maybe a little bit of jitters due to social anxieties, you might actually be able to perform a little better, but that very quickly starts to drop off. This is drive strengths as drive strengths increase. So the idea being that if you're a person who isn't likely to be affected by anxieties, then you can still perform in this kind of relative area. But then as it gets higher, your anxiety goes up, this curve comes down, so you become less and less and less capable of making those kinds of controlled responses. So these were the results again. We got a pretty good matching. I'm not necessarily going to go into that. I'm going to spend a little bit more time over here though. This calculation right here was done using, these are the results from the simulation. This particular calculation right here was done using those cognitive control estimates and the accessibility bias estimates. But also, you can look at what the values were from the MCS, right here, and that can also be correlated right here. And also, down here, you can look at what the biasing was in the bottom level, basically what the activations were for tool and gun based on when black prime or white prime was presented. So, and we found we're able to capture most of the significant results. So, implementing that, that's right here. Implementing that was done over here, and so here we have a public and anticipated or a private and an anticipated public, which we just call public here. We'll look at the participants one at a time. We've got some kind of, these are values for accessibility bias estimate. which are kind of targets that we want to pre-train the bottom level to do. That is, when black or white prime is matched with a gun, at about what rate do we want to, and in fact, at what rate do we want to match a black prime with a gun feature, and at what rate do we want to match a white prime with a gun feature? When we choose a white prime, what rate do we want to associate with a gun? What rate do we want to associate with a tool? And of course, we can vary this around a temperature so that not every agent has exactly the same bottom level of their ACS trained. We also set up a trainer. This trainer is actually going to help us to train up our neural networks. So this particular example actually uses the bottom level, or actually uses the implicit component initializer as part of the task. So we will actually look at that as well. Let me get down into the actual setup of the task down here. So what we do is we have these groups and we initialize these groups, then we initialize the agents and we test them and then kill them and remove them from the world. But so down in the world we've got dimension value pairs for things like skin color, black and white, nose shape, nose length, eyebrow shape. Now I know I'm not putting in pixelized versions of these pictures. You know, what we've done is that we have featureized them, but you know we put in this kind of featureized information about the primes. Here's some featureized information about the target. So handle, color, shape. Of course, these are black and white pictures, so the handle color is either black or white. Shape, whether it's bent or straight. Handle length, if it's long or short. Now these features were all we came up with all these features by actually looking at the primes and targets themselves. So the primes and targets that were used in the task were used to come up with these features. You know, it wasn't trying to reinvent any new information. That's why you don't see anything here in like anything here related to let's say hair color, right, or hair length, right? Because if you look at the actual primes, it's just faces. Okay, and it was done that way on purpose to try to get specifically at kind of the features that are important for the stereotype.
How did you come to that conclusion? And I don't so much mean just in this scenario, but I don't understand that about modeling in general. How did you decide how many factors you had to care about? Did you decide up front, this is what we want to study, so these are, or this is what we think matters, or did you?
Well, I didn't make the decision about. I didn't make the decision about the features. The features of the faces were a decision made by Jacoby when they originally did this task. So this is not.
How did they do that without a computer? Like, did they
did
get a lot of photos?
Well, I mean, they took these photos of, you know, of people's faces, and they give, you know, I'd say go to the Jacoby paper if you want to know, have a long, receive the full discussion, I guess, of the decision for why just focus on the face.
But I mean, like, so are you saying that they looked at eyebrow shape, for instance, and they picked a photo?
No, not at all. No, they were looking, this is just a featureization of the pictures the way they were presented, okay? So for the sake of modeling within Clarion, it's usually easiest, especially if you're dealing with these types of, it's usually easiest to featureize your world. You can do it at any level of granularity. I mean, I certainly could have created, you know, 1,000 dimension value pairs to represent 1,000 pixels in the picture, right? But when it comes down to it, it's not really going to add anything for me to give a full pixelized representation of that particular item. So what I did is I looked at the 4 to 8 different pictures that were in this particular task and said, well, what are the identifying features of these pictures? So, you know, the most important was actually skin color, right? I mean, you know, either black skin color or white skin color. But nose shape also seemed to be an identifying characteristic. Eyebrow shape is an identifying characteristic for telling women from men in the absence of, let's say, hair color. Or not hair color, hair length. People are actually very good, even with these zoomed in faces, of being able to identify differences between a male face and a female face. Eye size, these are kind of main features which relate, at least this was, I guess, in my own opinion, right? Main features that would relate to making biased judgments. But for the sake of the task, you could actually just get rid of all of these features and just go with skin color, because it really is the most identifying feature. And most easily and immediately identifiable feature difference. And there was no, for example, that within the actual task, there was no significant difference in terms of this association, in terms of the sex of the prime. They actually looked at that and didn't see any difference. By the way, the big difference between the Jacobi, the way they tested it in the Jacobi paper and the way they tested it later on in the Lambert paper is that in the Jacobi paper there was no time limitation. And so, and in the Lambert paper there was this time limitation. So the findings were slightly different. And then again here, these were kind of the most identifying features I could see when you were actually looking at the picture. So, the pictures where you had 4 different guns, which were mostly, in fact, in all cases, they were handguns. Okay, and the tools, which were, I think, in 3 out of the 4 of the cases, they were like pliers or wrenches, and then in one of the cases, it was like an electric screwdriver, which had kind of a bent. And in our own findings, our own kind of attempts at modeling this task, or verifying it within human experiments, we found actually that by and large it was that particular tool that people were making the error on. So the shape plays a bent or straight plays a very, very big role in the target. So and then actions, of course, is just identifying a tool or a gun. This simply just generates the faces. If you look at all of the different black faces or white faces, they have slight variations. There's 2 male and 2 female for each prime. Okay, and so we have all those features, and then you can see each one of these faces and everything have collectively, I think, a kind of a unique representation in terms of their features. So at least Clarion itself wouldn't see any 2 patterns that were the same when identifying or when being presented with the primes. And here's the same kind of generation for the guns and for the tools. So then you add the inputs and the outputs. In this particular case, we created a trainer, and I'm going to show you the trainer here in a second, out of a thing which is called a generic equation. Now, in terms of customizing, a feature of advanced customization is your ability to create your own implicit components. The by and far easiest way to do this, to accomplish this, is to use a generic equation. Now, the generic equation can be found in the extension folders, extension namespace of the Clarion DLL, Clarion Library DLL. And what it essentially just is that it is a framework for creating your own generic equation, where you will be given, let me find the code for it, where you'll be given, where you provide a delegate. you provide a delegate equation to this generic equation framework, and then it'll pass out the information for you. All right, it'll pass out the input, give you the inputs, and your job is to set the outputs based on the inputs, and so you can perform really whatever equation you want to perform on the outside. It's the easiest way of doing, creating your own customized bottom level component, because it allows you to just define a single algorithm, and the system will then pass you the task of doing the input to output translation. So that's utilized here in several places, both in the trainer and in capturing that hyperbolic tangent function within the MS. Now this was early before the drive equation was before we came up with the drive equation, and so for this particular task, it was useful that the hyperbolic tangent function seemed to capture the dynamics of the task. There's really no basis to why the hyperbolic tangent function was used, though, over anything else, other than it was just an early experiment in looking at how drive strengths are manipulated by contact, by the combination of stimulus and deficit. So, but I will show you within here how you can actually create that kind of, how that hyperbolic tangent function is created within here. So we set up this trainer here, just with its inputs and outputs here. The trainer itself is just providing that probability-based correlation between skin color and the skin color and tool and gun responses, and that was based off of these kind of accessibility bias estimates. So we set up the agent, all right, give them in this particular case, it's not an online learning task. There's not feedback, okay? The only feedback that the participants would receive as to whether or not they were right or wrong, or actually they didn't receive any feedback as to whether they were right or wrong in their tool gun responses. But the only real feedback they receive is they get a red X if they didn't respond on time, if they didn't make a response within the window. And all that really does is kind of re-up and sustain any type of performance anxieties. Although I don't think it had any real effect on the task. In fact, we did an experiment where the way we tried to manipulate participants was by inducing a competitive environment, which looks at their motivations for recognition and achievement. And what we found was that the introduction of competition, although people would report to a significant amount that they were affected by it, or that they believed the cues to induce the competitive environment, and they did show a significantly higher, at least in self-report after the task, they showed a significantly higher sense of competition than in a control group. Than in the control groups, we did not see the same type of effects in performance or degradation of performance, which led us to believe that this may be related mostly to avoidance-oriented drives. Anyways, so in this particular case, we can set up the inputs and outputs. Now, notice we're using a different method than just simply adding these DV pairs one at a time. You can also do an add range. This is similar to how you would add a bunch of items into the list of any regular collection in the C# library. So you can also do this add range, and it'll add a bunch of dimension value pairs. Then we can commit the neural network. Here we're setting up rules in the top level. Okay, so the way we've set these up is we go through all of the tools, and we're creating a rule for each of the tools here to say when this particular declarative or when this particular tool is set to true, then we're going to go ahead and respond with a tool. And so we do that for all the tools. We do it as well for all of the guns. All right, now in this particular case, we're setting up just RER rules. And you say, well, why are we doing this with RER rules? Well, we don't need IRL or fixed rules in this particular sense. Yes, these are for the sake of conceptual speaking, fixed rules, okay? But the association is a simple input pattern to action association. So there's no reason why you can't set up a simple refinable rule and place it in the top level of the ACS, and then simply just turn off refinement, and that will prevent the rules. And also I believe, I'm not sure if I put that in here at this point, you can also add in perform deletion by density. So that will prevent these rules that were placed in the top level from actually being deleted. So they won't go anywhere. And to that extent, I believe as well, and I may prove myself wrong here, but you can also do it at a what is it? Perhaps not. I thought I had added it in by this point to all of the rules. But there is a way for you to set the rules themselves so that the individual rules themselves can be not deleted as well. So, anyways, so in this particular case, we have these rules on top level, and we have these. We have the neural network set up on the bottom level. Here we set up our honor drive. So this is similar to how we did it last time with the Hello World full task. That is, we say that we want to initialize a drive. We choose the honor drive. Specify a initial deficit. Now remember, in this case, the initial deficit is kind of a normalized distribution, so we're just going to have it randomly pick a value in between 0 and 1. Now I know that doesn't necessarily give you a guarantee of a normalized distribution, but with enough participants, and the actual results that were published, I believe, used 100 participants in each grouping. So with enough of them, it gives a good enough representation. All right, so in the drive component, we're actually going to use the generic equation. Now remember, before we would use something like the drive equation. In this case, we're going to use the generic equation, and we're going to set it up within this honor drive. Okay, we use the generic equation factory, and then what we do is that we have this equation delegate. Again, the equation delegate just takes in an activation collection for an input and an activation collection for an output, and your job is to take the activations on the input side and translate those over to the activations on the output side. So that will give you, so we implement a tangent equation, all right, and let me simply go to that. Here, where the output is equal to a value related to the tangent equation. So this is just the hyperbolic tangent function. And it sets the activation of the drive strength equal to the value equal to the value of the gain, the value of, where is this? This is the value of the deficit times the gain, and I believe in this particular case we were using the gain. I don't know why we used the gain there. That must have been, I don't think that was supposed to be there. I believe that was actually supposed to be the stimulus. anyways, we use it to, we perform basically a hyperbolic tangent function, which is the individual differences value times the stimulus, which is or times the presentation of whether or not the person is being stimulated with a cue that induces, let's say, honor, right? It induces a social anxiety type of need to adhere to these social norms. So in the case of anticipated public, the idea that they were going to have to share their results. Okay, so we then the other thing we do here is we create a parameter change action chunk. All right, and our parameter change action chunk is used over here in the accessibility level probability setting equation in order to change the parameter. Now the parameter that it is changing this was actually just a relic, a leftover relic of a previous demonstration. The actual level, the ACS level probability setting equation itself already gives you the appropriate actions within the output of the equation. Okay, but the idea here is that what it's doing is that it's using parameter change action chunks. Now the parameter change action chunk is exactly what it says. It's an action chunk that will change the parameters within some sort of component. So if I wanted to actually set this up on the outside or demonstrate how this would work on the outside, all right, the way we would do this is we would say this parameter change action chunk that I've created dot add, and within there, one of our options is this kind of long string right here. Well, what this does is this allows you to define a parameter that you want to have changed. So what you first do is you say, well, what is the target thing that I want to have changed? So in this particular case, I want the participant's ACS is going to be the target of my parameter change. All right. What is the name of the parameter? So it's just the straightforward name. But if of course, if I want to look it up. So in this particular case, I want to have it change the selection measure for the RER. But I want it to be changed by the MCS, so I'm going to have it change that parameter. This is a specific to the ACS. Now I could just have it change the straightforward selection measures, but this allows us to both have the MCS tune the selection between the top level, as well as allowing us to have variable or fixed tuning. So our top level and bottom level can still be tuned by, let's say, success rates, for example, or whatever we want to use in terms of variable or fixed to set an initial value. So I say I wanted to set that, all right, and then I can say, well, all right, what value do you want it to set it to? And in this case, let's say I don't really care what I'm going to have it set to. If I don't specify anything, basically what I'm saying here is I'm saying that I want it just to set it based off of the actual value, the activation of this particular action. So that's saying that I don't want to set a fixed value, that I want it to be set variably based off the activation. Now, the activation of the action. So whatever this is appended to, if it's appended to a neural network in the MCS, then whatever the activation on that side of the network in the MCS, that will be what the parameter value is set to. Okay. If I wanted to actually say, okay, actually set this parameter to 0.5, I can do that, and then whenever this action is chosen, it'll actually set the parameter to the specified value. That allows you to have a more discretized changing of parameters where you can say, in some cases, set the parameter to 0.5, in some cases, set it to 0.75. The reason why I point this out is because actually, any action can also be a parameter change action chunk. So, in the case of where we're doing, if we were to, let's say, be working with the NACS, we can, on top of initiating, let's say, a new round of reasoning, all of our actions will have the same kind of ability to specify parameters. Okay, and what happens is that in addition to performing whatever the action is, that is specified by that action chunk, it will also tune whatever parameters you specify at the same time. In fact, it'll tune it ahead of time before it'll initiate the associated action. So let's say, and I can't think of a concrete example where you might want to do this, but let's say you want to set a goal, but you want to actually change the nature of the goal structure at the same time, right? You can chain those two together by saying, change the parameter in the MS from a goal stack to a goal list, or let's say change the capacity, and then at the same time, add a particular goal into the goal list, or into the goal structure. That's a simple example. I don't know exactly where you would actually do that, or how you would justify it within a cognitive standpoint, but it does allow you to do that kind of thing. So it's most useful, I think, when you're talking about the NACS, because you can say stuff like, initiate reasoning, but only use the top level, and make the conclusion threshold equal to 0.5, and then run 4 iterations of reasoning. Okay, so you can do that kind of stuff where you can chain all of those commands together within a single action, and it'll initiate all of those parameter changes ahead of time before it initiates reasoning, and then it'll go and continue by doing reasoning. I'm showing you this on the outside because I want to demonstrate to you how this parameter change action chunk works. When it actually gets down to it, though, what we're doing here is we're actually using a parameter setting module, which comes with the system. It's a generic parameter setting module, which means you can use it to set any of the parameters. In this particular case, we're using this generic parameter setting module, but what we're applying it with is we're applying it with a level probability setting equation. So we have an equation which is set up for this inverted U curve, okay, that was demonstrated previously. And that particular equation, which is a sample you can use in the extensions folder, out of the extensions folder, will automatically set up the system to to calculate the level probability in the ACS using this inverted U curve. And to set that up, all we have to do is we specify that we want it to be placed into our parameter setting module, which we've named LPM. All right, we want to use the factory. And then the other thing you have to specify as part of this probability setting equation is who the particular participant that is going to be the target of this particular equation. And this is simply just to check to make sure that you're not trying to, excuse me, it's used in order to be able to find the particular agent's ACS. From this, see how we do it in this command above, we pass it the specific target object. This particular ACS, we're going to want to have it change this parameter. So, and of course, this thing will also check to make sure that you're not trying to tell one agent to set another agent's ACS. So you can try to be tricky, but it won't. It'll give you an error. The only thing we have to set within this equation is what are the particular drives, or what is in this case the particular drive that is going to be used as part of this equation. In the case that we're using multiple drives, if I remember correctly, I believe the probability setting equation uses the max function. So the max of the particular equation, or the max of the drive strengths, is the one that is used within that particular equation. So we then commit the equation to the module, commit the module to the participant. So it's all fairly straightforward, the way you've seen it before. So and then what we're going to do is we're actually going to go and pre-train this particular neural network before we set it. Remember, this is not an online learning task. We're not looking at how performance gets better as it's related to learning online. So we do have this neural network which we've said, but now, of course, we need to train this neural network. And it looks like in this particular case. Yeah, so what I do here in this particular case is what I do is I create a data set where I grab a bunch of activation collections. And what I'm going to do is I'm going to basically be combining together every single combination of the prime and every single combination of the target. And what I'm going to be determining is at what probability am I going to be saying that a particular prime and target combination relates to, at what probability a particular prime or particular target combination relates to the identification of either a tool or a gun. So once I've set up these, this is basically allowing the neural network, which again what we're assuming here is not so much that the bottom level is being trained to these particular primes and targets, and I'll show you how that's made more specific in the actual trainer. But the fact of the knowledge of a gun, or the experience of a gun, and the experience of particular primes being associated with the particular guns is the data sets that we're really setting up in these particular examples. So I've created a bunch of data sets here essentially, and what I've done here is I'm going to use the implicit component pre-trainer. Now what I'm going to say, to use the implicit component pre-trainer, it's actually fairly straightforward, although it can certainly sound a little confusing when you first try to use it. All right, what you see here is a whole bunch of options that you can set within the train function in the implicit component pre-trainer. But when it comes down to it, it's fairly straightforward. That is, given a particular target implicit component, which can be a neural network, it's anything which is trainable, anything which can be trained. You specify a target, the thing that is going to be trained. You specify a trainer, all right, which is the thing that is being trained, or that is acting as the trainer. Okay, the thing that will be providing what the appropriate output pattern is given a particular input pattern. All right, and the input patterns were all set up here. All right, that's what these data sets are, is just setting up what the input patterns we're going to use to do our training is. And then we have, after that, the other thing you have to specify is the data set. So what is the data set that I'm going to be using? So those are really the three main things you have to provide. So here are the patterns of inputs that you're going to be providing. The trainer will give the appropriate outputs, and the target will be trained based off of that. We can then specify a bunch of different things, like we can specify a training termination condition. So there's a couple of different built-in ones. By default, it's fixed, which basically means that the thing will terminate after a fixed number of iterations, all right, which you can specify by the number of iterations. Another option is that you can have it terminate by a sum of squared error. That means that when the sum of the squared error in the output of your network, or of the network that you're training, falls below a certain value, falls below a certain threshold, when it's trained to a certain level of precision, then you can have the training cease. And your other option is both, which is either train it until it reaches a precision, or until a certain number of iterations are performed, whichever comes first. And so those are kind of the three termination options you can use that are built in. The other thing too is you can specify things like a selection temperature, which basically says if you're using, for example, something which is online trainable. Let's say you're using a simplified QVP network, but you want to give it a little bit of already defined knowledge before your task starts. You can set it up. You can set up a trainer and have it train it as if it was a runtime, as if it was already in runtime, and you can specify what you want the selection temperature to be for doing that type of pseudo online training. The other options, you can specify whether or not you want the data set to be traversed in random order, so that you're not looking at the same pattern, the same input pattern in the same order each time. That's actually somewhat important for backpropagation networks. And also you have an option to test, to do only a test. So you can send it a training thing, but basically you can tell it not to perform any learning, just to perform a test. So what it would, in this particular case, what it'll pass back to you is what the sum of squared error is. It'll perform a single iteration through your data set. It'll calculate up all of your, your sum of squared error, and then it'll pass back to you performance statistics, so that you can know, let's say, how well your network is trained, or how well it's operating based off of a data set. That can be useful. Sometimes, let's say, if you have a separate data and a separate training, or a separate training set and then a separate test set that you want to make sure that the training set can then capture. So you could run one round of training, and then you could set the thing back up, send back in the target, the trainer, and your test data set, and say just do a test, and it'll run through the thing once, and it'll come back and say how close did it, how well did your target network capture the results as it's reported by the trainer. Does that make sense to you guys? Because I know that in general, training a neural network, training an implicit component, can oftentimes be very time-consuming, and setting up the actual training, the offline training of a neural network can be confusingly difficult. This was done in this component, implicit component initializer, was created with specifically to try to simplify this whole process for people. So instead of having to write your own code to run through really, large, having to run through really large data sets, or having to actually do the setting of the network, and then the back propagating, the learning, and then having to look at error rates, or having to look at all of that kind of information. The trainer handles all of this stuff for you fairly easily, basically by giving it the network, giving it a trainer, and then telling it how many times you want it, a data set to train over, and how many times you want it to train, or to what precision you want it to train. And what you get is, after you exit out of this training method, is you get this thing having been trained to report your data set that you specified. So in this particular case, we're just doing it for a certain number of training trials. We're doing a random traversal. Each training trial is one complete time through the data set. So just keep that in mind. And yeah, so that, in this particular case, that's what we do. Then when we actually get to the test, what we do is we present the primes and the targets. We do it to the number of test trials that were performed in the human experiment. Okay, we have it present a prime and a target together. We shuffle up the prime and the target, although we do it in an organized way, because for each block of times through the target and the primes, each target and prime is paired with each target is paired with each prime twice. So we keep track of that in our shuffler. We're going to create sensory information, all right, where we add the primes and we add the targets. And then we go and we set a stimulus. And in this particular case, what we've done is we used, remember earlier I said I thought it should be the stimulus. In fact, if we come back through and we look at this, the gain is actually being used just in this particular example to help train the or to help determine whether or not we're in the public or the private setting. The idea being that gain has been tweaked earlier on in the task, so it's not being stimulated each time through. It was set prior to the task. Prior to the task, the agents were told, yes, you're going to be in this particular grouping or not. Technically, it doesn't really matter though. We could just do it with the stimulus, but in this particular case, the way we're performing it, we're giving a certain amount of stimulus, and then we're going to have it perceive. It'll choose an action. We'll determine whether or not it was a tool or gun. We're going to record whether or not it made an error. So in this particular case, for example, we're going to see if it chose a tool and the tools doesn't contain this particular target. It means that the participant made an inaccurate judgment on a gun trial, which means we will give it an error. So if it was if the prime was a black prime, then we'll say it was a black gun error, otherwise a white gun error. And same thing for tool, that if it chose a gun, but it wasn't supposed to be a gun trial, then we'll say that it was either it was a black tool error or it was a white tool error, depending on whether the prime was black or white. At that point, the results have been reported here. This is just going through and reporting all of the results in a way that can be easily copied and pasted in a tab delimited string format into, let's say, Excel or some other SPSS if you want to do analyses. And that's it. So the particular of the pre-training equation, let me point out that in the pre-training equation, remember what we were talking about here is that the bias was mostly related to the target, was mostly related to the skin color. So in this particular case, what we've done here is that we set way back up when we were initializing the agent, we set up a probability accessibility bias estimate probabilities for black and white. And what we do is, if it's the input relates to a black prime, then we're going to say if at random, if at random, or I guess at a probabilistically randomly chosen value, set the gun or set the tool. And over the course of the training, approximately, in this case, if I'm not mistaken, I think the number here was like 0.58 plus or minus 0.03. So somewhere between 58 and 61%, 55 and 61% of the time, it will associate a gun with a black prime, and the other percentage of the time it'll do it with a tool. And the same type of probability variations are set within are set for the white. So that's how that particular pre-training equation is run. And of course, that pre-trainer, that implicit component pre-trainer, or excuse me, implicit component initializer, the train method there will of course call this function, or call this equation when it wants to, or when it's asking the trainer what the appropriate outputs are given the input that's passed in. So that's a lot to go over, but are there any questions?